In this section, we're going to continue on talking more about probabilities with the topics of conditional probability, more about the intersection, and another topic called independence in probability. And to start out with conditional probability, we have a new notation here. It says that for conditional probabilities, they happen when the probability of one event depends on the outcome of another event. For two events A and B and within a sample space S, we define the conditional probability using this notation. The probability with the letter P, but we have the A with a line next to it, separating it with B. And this stands for the probability of A given B. So that's how we read that new notation here. And it gives us a formula to do it. It says the probability of A intersect B divided by the probability of B. Let's look at that here in this next example. We're going to use the standard 52 card deck again, starting off with if the card is a spade, given that it is a 7. So the situation here is if we start by drawing a 7, then it limits the chances of it being a spade. So that's what we mean by its conditional probability. The 7 is a condition that affects the probability of it being a spade as well. And so let's go through the possibilities here. There are a total of 4 7s. And there's only one 7 of clubs. So that means we're limited down to just one 7 of clubs. So when we talk about the probability of a spade given a card is a 7, then that would be with the notation of probability of spade given a 7. Okay, and so that's going to be equal to, by the new formula, the probability of a spade and a 7 divided by the probability of a 7, which is equal to 1 divided by 52, that's the probability of it being a spade and a 7, divided by 4 divided by 52, that's the probability of it being a 7. So if we reduce out the numbers and reduce it down into lowest terms, it would be 1/4. The next one we're going to say if the card is red, given that is a spade. So let's use the letter R to stand for the card is red. And there are a total of 26 possibilities here. 26 possible red cards. S can stand for the event that the card is a spade. And the probability of them both happening together, probability of R and S, which is the probability of R intersection with S. There are 0 red cards that are spades, 0 out of 52, so the probability of intersection is 0. And the probability that it's a red card is 26 out of 52, or 1/2. So what that means is the probability of a red card, given that it's a spade, the probability of R given S, by the formula it tells us is equal to the probability of R intersect S divided by the probability of R, which we just said the probability of intersection is 0 divided by the probability of R, which is 1/2. And that's just equal to 0. So there's a 0 chance of this happening, which makes sense in the long run. But if we think about it, but this is just showing how the formula functions in a case like this as well. On this one, it says, use the table on the right to find probability of A, probability of B intersect F, and the probability of D given C. where the events A, B, and C are mutually exclusive, as well as the events D, E, and F. These are all mutually exclusive events here. So in other words, the events cannot happen at the same time, which makes it a little bit easier to work with. Now, starting off with probability of A. Probability of A is the column. Notice we have the column for A here. So the probability of A would result from just putting together all those probabilities to the total here. Probability of A. So that would be 0.70. Since A contains all the other events for D, E, and F added together. Okay, and then the probability for the other events here, say for B and for C, would also be determined by their respective columns. And for the probability here of B intersect F, we'll look at B and we'll look at F and we'll find out where they overlap with each other. Looks like they overlap here with 0.02. So that's the probability of B intersect F. If we want to do the probability of D given C, probability of D given C, we have to look at the formula to do that. That would be the probability of D intersects C divided by the probability of C. We look at the chart or the table to get the probability of D intersects C. That would be up here where the two overlap with each other. So that would be the 0.07 for the probability. That goes here on top. Probability of C is the 0.18. So 0.07 divided by 0.18, which when divided and rounded off is 0.39. For example 3, we're dealing with a car manufacturer which produces 90% of its cars at plant A. If 7% of the cars manufactured at plant A have defective emissions control devices, what is the probability that one of this manufacturer's cars was manufactured at plant A and has a defective emissions control device? So let's highlight the words here. Plant A and has a defective emissions control device is what we're looking for here. So let's let the letter A stand for the event that the car is from plant A, and let B stand for the event that it has one of these defective emissions control devices here. What we want to find is the probability of these two events happening at the same time, event A and event B, which is the probability of A intersect B. This gives rise to the new formula that we have above called the product rule. For events A and B with non-zero probabilities, the probability of A intersect B can be done either as the probability of A times the probability of B given A, or we can do it by the probability of B multiplied times the probability of A given B. So that's what we're going to use here in this case. The probability of A intersect B, I'm going to calculate it by the probability of A times the probability of B given A. So what I can say here is that the probability of coming from plant A is 0.90 since 90% are manufactured there. And the probability of B given A is the same thing as saying the probability of having a defective emissions control device given is from plant A, which we can say that that is equal to 0.07 since 7% from plant A have the defective part. So what does that mean? Well, it means again that the probability of A and B, probability of A intersect B, would be the probability of A times the probability of B given A, which would be equal to the numbers we have up above, the 0.90 times the 0.07, which is going to be equal to 0.063. Now we reach the topic of independence of events and probability. It says that if A and B are any event in sample space, we say that A and B are independent if the probability of A intersect B is equal to the probability of A times the probability of B. And this example here is going to help us test for that. So let me write down exactly, again, what we mean by independent versus another word, mutually exclusive events. So the overall summary here is we now have the idea of independent events and mutually exclusive events. And they are different because independent events talk about events where one outcome of an event does not affect the outcome of another event. They're independent in that case. On the other hand, mutually exclusive refers to events that cannot happen at the same time. So these are related but very different topics that we look for when talking about probabilities. And so let's look at the dependence here in particular for this example. Okay, now to get started, let's talk about the probability of A. The probability of A is going to be the total down here of column A. So 0.20. The probability of E is the total of that row for row with the E. So 0.30. So what we're checking for first off is probability of A times probability of E. That's equal to 0.20 times 0.30. And that's going to equal to 0.06. To test for independence, we'll also check the probability of A intersect E. If we look at the table, the place where they intersect, where they overlap with each other, where A and E intersect is right here. So that's also equal to 0.06. So as a result, we can say since the probability of A times the probability of E is equal to the probability of A intersect E, A and E are independent events. Here's another table of data we're going to work with for probabilities. And this table, what it shows is the colorblind versus not colorblind for male and female. First thing we're going to do is take the numbers that we have here and turn them into a probability table. Because right here we're not dealing with probabilities in the table, but just the frequencies, how often they occurred. So keep in mind that there are 1,000 people that were in this study. And let's set up a table with the probability. So let's see how that goes. Okay, to get started, the way we're going to convert our numbers from the table into the probabilities is I'm going to take the frequencies, which first one here is 6, and divide it by the total number of 1,000. 6 divided by 1,000 will get 0.006. Okay, and that corresponds basically to the probability of colorblind, which in this table they're using the letter C to stand for colorblind, and the complement to stand for normal. And we do that also for normal, which in the table there's 650 of those out of 1,000. So that's going to equal to 0.65. And I'm going to go through the table and do this division for each thing. So for the totals, 656 females out of 1,000. Divide those, it's 0.656. And then for the males, I came out with 0.035, 0.309, 0.344, and then for the totals column, 0.041, 0.959, and 1. Now the first question says, what's the probability that a person is a woman given that the person is colorblind? So the first part here, we're going to find the probability of being female given colorblind. And the probability of that can be done with the formula as the probability of F intersect C divided by probability of C. If we look at our table, the probability of being female and colorblind is 0.006 divided by the probability of colorblind, which is 0.041. And if we divide and round, we get 0.146 for that probability. Part C asks for the probability of somebody being colorblind given that they're male. With the formula, we do that for the probability of C intersect M divided by the probability of M. The probability of colorblind given it that they're male is the 0.035, colorblind and male, divided by 0.344. I divided and rounded to 0.102. Now the next part asks, are the events of color blindness with male and female independent? So let's talk about that. So for the next thing to figure out if it's independent or not, we take the probability of color blindness times the probability of male, which from our table, we can look that up here. Probability of color blind is 0.041 times probability of male, 344. And that's equal to approximately 0.014. To check for independence, we also compare with the probability of the intersection of the two, probability of colorblind and male, which if we look up at our table at the colorblind and male, that was the number for 0.035. So these are not the same, however. So since these are not the same, then that means that the events are not independent. If we do the same for male versus female, the probability of color blindness times the probability of female. Probability of color blindness, 0.41, times the probability of female, 656, comes out to be approximately 0.026. And probability of colorblind intersect female colorblindness and female is, if you go to the table, 0.656, which again, two numbers which are not the same. Again, that means that these events are not independent, which kind of makes sense when you think about it. Colorblindness is dependent upon gender. And so we look at the events occurring and they don't occur separate from each other. One does influence the other. This next example, we're going to compute probabilities using the probability tree. And so let me highlight what we can do with this probability tree. So each branch along the tree has a number, which is the probability of that event happening. So the probability first of M is the 0.08, and the probability of another event that could occur first, N, either M or N. For N, the probability is 0.92. Now, if we go to the next number after M or N, either event R or S could occur. And so we have to look at these probabilities here to know how likely they are to occur each time. So the probability for R, we write it as the probability of R given M if we travel along that branch in the tree. M comes first and then R given M, or the probability of S given M, or the probability of R given N, or the probability of S given N. So given either M or N have occurred, we can see the probability that either R or S will occur here. So the tree shows a sequence of events with the probability of the first event, then following the probability comes next of the next event that could occur after the previous one has occurred. And so in this question we want to find the probability of M and S. The formula again for the intersection, probability of M intersect S, is the probability of M times the probability of S given M. And we have those numbers in the tree. For M, it's 0.08 times the probability of S given M, which is 0.94. And that comes out to 0.0752. Now the next one it wants me to find is the probability of R. Now the thing about the probability of R is it depends on what branch you follow. But to get the probability of R in total, we need to go through both branches. That brings us to R. The way we can do that is to do the probability of M intersect R plus the probability of N intersect R, because M comes first, then followed by R, or then N and R could occur. So to do the calculation, we have our formula for each of these. The probability of M times the probability of R given M, that's the first part here, plus the next part where we have the formula that goes the probability of N times the probability of R given N. We have those probabilities up above, 0.08 times 0.06 plus 0.92 times 0.14. And that all equals out to 0.1336. An alternative way to do what I just did is to take the probabilities along each branch that leads you to R, multiply those probabilities together, and then add up everything. So we have two branches that lead us to R, so we can take the 0.08, multiply it by the 0.06 from the first branch, and add that together with the other branch to R, which has 0.92 followed by 0.14. Multiply those, add them with the other branch, and you come out to having it equal to the same 0.1336. That's an easier way usually to remember how to get the probability of R to go along each branch separately, multiply, and then add up everything.